All right. Good morning, everyone, and welcome to Montreal for those of you who are from outside Montreal. My talk is actually going to be a bit of a different flavor from most other talks you might have seen or you will see in the rest of the workshop, because my talk is going to focus more on the multimodal aspect of building agents and not so much on the agents itself, like computer use agent or the web agents. So let's see what I'm going to talk about. So first I'll talk about how can we build multimodal agents for the task of language-guided image editing. And for me, the definition of agents is basically models that take actions and then trained using reinforcement learning. After this, I'm going to focus more on the multimodality aspect. So I'm going to talk about how can we improve the data efficiency, particularly of the multimodal instruction tuning stage when we build multimodal large language models, which is really relevant for us working in academia because we don't have large resources to train models at scale. And an important part of building and training agents or models is also making sure that their performance aligns with human expectations. I'm going to talk about how do we assess the degree of alignment of the behavior of models with human expectations. Okay, so with that, let's get started. As I said, I'm going to talk about the language-guided image editing task first. So let's look at why this is a complex reasoning task and what are the different paradigms of tackling this task of image editing, and basically what we found to be the most effective paradigm, which actually is RL-based. Okay. So I'm going to show you some examples of different kinds of image editing tasks. So here is what we call a simple edit. So broadly speaking, we are going to classify the types of edits into two categories, simple and complex. So here it's an attribute edit where the request is to change the color of the picnic basket. And here, the expectation is that the model will only make the change that is requested and do not make any other changes, right? So for example, it cannot change the background, it cannot change the sheet which is under the basket. It only and only has to change the basket, and that to the color of the basket and nothing else. Okay? And surprisingly, this is, those of you who are not very familiar with image generation or image editing, this is something that models struggle with. So they struggle with sticking to the instructions and not going beyond what has not been asked in the instruction. Here is an example of a complex edit. So making any kind of pose changes or any kind of motion changes are actually quite difficult for models, not as simple as changing just an object or an attribute of an object. So here the ask is to tuck the hand of the woman into her lab coat. So model needs to do it in a reasonable way, and again, for that they need to have understanding of human poses and basically not change anything beyond what is asked in the instruction. Counting is a famous example of kind of skill that models are not good at. So Elaine talked about my work in VQA back in those days. And since then, since I don't know what 2015, this has been a very challenging problem. Models are just not good at counting, be it VQA kind of models, and the recent versions are multimodal large language models, or be it image generation or image editing kind of models, right? And similarly, spatial reasoning has been a long-standing challenge for a long time, to be able to understand both absolute spatial positions and also relative spatial positions of objects in images, and also grounding that, connecting that with language, right? So swapping the position of two birds here, it has to sort of understand what that means and do it faithfully. So all of these, it might seem like a very quick edit for human. For models, these are actually quite challenging. Okay, so now speaking of what are the typical paradigms of tackling this task of image editing. So the most common one is supervised fine-tuning paradigm, where a lot of the work in this space focuses on building image editing models for specific type of edits. So either training the model for just action edits or training the model just for object and attribute edits, and so on. So of course, this is not general purpose. There is this other line of work which tries to provide a little bit more inductive bias to the model, which is providing bounding box conditioning. So basically, not just giving the image as the input to the model, but also giving the bounding box coordinates of the objects that are supposed to be edited. So either these are human-provided bounding boxes, or you can use an object detector and then locate the boxes and then use that as part of the pipeline. So the point of doing this is to ensure the model does not make any changes outside that region of bounding boxes, right? Because as I said, these models have tendency to make other edits which are beyond what is specified in the instruction. So the problem with this approach is it's not end-to-end. Either you need extra input from the human, or you have to do it in a non-end-to-end manner. So when we started this project, we were asking a few different questions. So we were very interested in finding out what is the most effective approach to tackle both kinds of simple edits and complex edits. Right? So simple ones are like just adding or removing an object or changing the attribute of an object, and complex edits are of the sorts of counting, spatial relation, action edits, and so on. And particularly, we wanted to do this in a unified end-to-end manner instead of building individual modules for different kinds of edits. And at the same time, in NLP, there was this, chain of thought reasoning, GRPO, RL, all of these were, coming up, and basically, people were not applying that for, particularly for, image editing. So we were sitting at this conjuncture, and we were wondering, can we use, the effectiveness of all these techniques? Would it be effective even for this task, which is, image-based task? You are generating an image, and you have to do this multimodal reasoning as well. So let's see what we found, and I'm going to walk you through basically our investigation in this. So this is a paper that's going to be presented at NeurIPS, and it's led by my students and also students from Siva's group and Chris Paul's group, and both Siva and Chris Paul are here as well. Okay, so we wanted to build on top of autoregressive multimodal model, and when I say multimodal, I'm talking about model that can generate both language and image. So we worked on top of this MO3 model, and the reason for using this kind of autoregressive multimodality model is because we wanted to explore chain of thought reasoning as well. So we needed a model that can not just generate images conditioned on language, but can also generate language conditioned on both image and language, right? So yeah, it's a standard autoregressive model, which is just teacher forcing, next token prediction, and it has been pre-trained for both the task of image captioning as well as the task of language conditioned image generation, right? Okay, so we tried basically three approaches here, and we were interested in seeing in a very controlled manner which approach performs better, and one of our sort of main focuses here was how do we achieve better performance for complex edits, because these are the really the more challenging ones. So SFT, basically you need paired data, so you have input image, language, edit instruction. So this prompt, we are going to call it edit instruction, and then we have edited image. So we have ground truth edited image, and a bunch of existing data sets have these. Either these are coming from humans, or by making some by running image editing models, but in a very controlled manner. And then we were interested in trying out chain of thought reasoning as well. So basically here the idea is we are supervising the model with thinking tokens. So we are supervising the model to first generate the line of reasoning that it would take to do the edit, and then predict the edited tokens autoregressively after that, right? And we basically curated this thinking data which we were using to supervise the model. So again, this is supervised learning, but the difference is the supervision is not only with respect to the final edited image, but is also with respect to the reasoning chain. And finally, we wanted to try RL, and as I said, this was a time when GRPO had made a lot of hype in the community. So basically here, there is no paired data. So that is one of the great benefits of using this algorithm. So we just have input image, we have the edit instruction, and basically we are just letting the model run the policy and then generate the final edited image, and we basically will use, and I'll talk more about what reward model we use. So we just have a 20 reward model, and then we don't need any paired data here. Okay, so I'm going to now talk a bit more deeply into the different settings to just give you a sense for what are the strengths and weaknesses of different models. So I'm going to skip over these details a bit. We had two types of both training and benchmark datasets consisting of simple edits, datasets consisting of complex edits, and these are the existing datasets from where we curated our simple and complex edits datasets. And basically, we tried a bunch of different things. So the first thing that we were interested in trying to answer is, can we teach a model complex edits, which is like counting spatial relation, just by utilizing SFT to the best we can, right? So there are different ways you can do SFT. You can first pre-train the model on the simple edits and then fine-tune on complex edits, or you can do it, in a continual manner as well. So we just wanted to see, like, what is the best we can get out of SFT with respect to improving the performance on complex edits, because for simple edits, models are actually not that bad. And overall, our finding, I'm not going to go into all the details of the results here, but basically overall the finding was it's very hard to teach complex edits to models just using SFT. In fact, fine-tuning the model on complex data was hurting performance. So we didn't have any success here, essentially. And then next we wanted to try, let's see if we can encourage the model to think about the reasoning process before it actually generates the final edited image. Maybe it will do better on complex edits, right? Because you can imagine, for example, the spatial relationship edit where I ask the model to swap the position of objects. You can reason about it. You can say, okay, object 1 is here, object 2 is here. You can predict the bounding box coordinates, and then you can reason about it. Okay, I'm going to have to change the coordinate of this object, bounding box coordinate of this object, and all of that. So here is an example of the kind of data we curated, although this is an example of a simple edit, but you can imagine similar reasoning chain for complex edits as well. So basically in this data, the model first talks about what is shown in the source image, what is the location of the object that needs to be edited, and then what is the kind of change that needs to be brought about, and finally what the edited image will look like, right? So we are supervising the model with this kind of data and also with the final image. And I'm going to skip all this. So basically, here we didn't have success either. We found that training the model with this kind of thinking data actually degraded performance. And one of the reasons for that could be that this MU3 model that we are using wasn't pre-trained for reasoning capabilities. And again, like talking about the complex data, we found that adding complex data with this kind of reasoning supervision further degraded the performance. And here is a qualitative example. So here what we are seeing is vanilla SFT without any thinking actually produces better results than SFT with reasoning. And if you sort of dig deeper into why this SFT with reasoning is not working well, is it because the reasoning chain itself is bad in the first place, or is it because the reasoning chain is fine, but the model is not able to apply that kind of reasoning when it is actually generating the image? So we found that it was latter. So I don't have time to read through this, but basically it does identify what is the object in the image, what is the bounding box coordinate. So you see we are showing the bounding box overlaid on the image here. It also reasons about what the new object should look like, but the final edited image is not very high quality. Right? I also wanted to bring to your attention that there is this paper Bagel which came out after we finished our work, and they actually did similar kind of chain of thought based supervised fine-tuning, and they show that they are able to improve the performance using that. However, when you dig deeper, you see that the kind of benchmark, the kind of editing task they are tackling is actually of a different flavor than the kind of editing task we are tackling. So here are the editing instructions that they are looking at. Can you provide an image of this car's interior? Are there phone cases available that match shirt design, and so on? So all of these editing prompts require some sort of external knowledge beyond just looking at the image, right? And you can imagine if it requires some sort of external knowledge, then using reasoning from pre-trained LLMs or multimodal LLMs would be helpful here. Okay, so finally coming to the solution that we found is GRPO-based RL post-training works pretty well. And it improves the performance quite a bit for complex edits, which is what we were targeting mainly, while at the same time we don't want to reduce performance on simple edits, of course, right? And another benefit of this approach is you don't need paired data. So it's basically the standard GRPO pipeline. You have input image, you have the edit instruction, you train a policy model, which is again this autoregressive MO model that we were using. You sample a bunch of different outputs, which is basically a sequence of tokens, right? A sequence of image tokens. And then we have a verifier, and I'm going to show you what that verifier is. And basically you do the advantage computation, and then you train the model based on that. So for the verifier, we used a pre-trained multimodal large language model, Quen. So we did not fine-tune it for this specific task of image editing. This was just a pre-trained model. And we used basically this existing VIE score, which checks for a few different things. So semantic consistency, as in whether the edited image is following the instruction or not, and whether the quality, the perceptual quality or the image quality is good or not, right? And I'm going to skip the training details here because of lack of time. So basically, cut short, the story is that when we do RL, so by the way, this is RL post-training on top of the SFT model, and that SFT model was trained on simple edits only. So in the RL stage, that is the first time model is seeing some sort of complex edits, and we see that it already improves performance quite a bit. And basically, like so far, we didn't have success in teaching complex edits to the model, either by vanilla SFT or by SFT with reasoning. But when we do RL with complex edit data, the model does very well, both on simple and complex edits. And these are some other settings, where we took different versions of SFT model and applied RL on top. In every case, we consistently saw that RL post-training helped quite a bit. So I'm going to show you these examples, which are more interesting, to show you where RL actually matters. So here, the instruction is add a ball to the left of the woman. So again, this is an example of spatial reasoning. You see the SFT model doesn't add a ball at all, and the RL model is adding the ball and also adding it to the left. Here, it's again an example of swapping positions of two items. SFT model just changes some visual attributes of one of the items. RL model is able to do the instruction following properly. And here, again, it's an example of accounting where you need to remove one board, and the SFT model removes both of them, right? And similarly, this is an example of action edit where you see that it's not very high quality image, so it's a bit hard to see, but basically, the door looks more open than in the SFT case. And finally, we did scaling up of this a bit, training on more examples. And when we did that, we were able to surpass the best model at that time, which was OmniGen model. And yeah, you can apply RL on top of SFT, on top of the thinking model as well. And there also we see that RL was able to recover some of the performance drop, which was a result of applying thinking on top of SFT model. So to conclude, basically, here we found that supervising with chain of thought reasoning, which actually we were quite hopeful about, does not show benefits in image editing performance, and GRPO-based RL post-training helps. And if you are asking at what stage of training should you introduce the complex editing data, then RL post-training stage is, from our investigation, we found that is clearly much more beneficial than introducing it during SFT stage. And at the end, we are basically released this end-to-end model. Remember, that was the goal, that performs well on whole spectrum of edits. And this is the strongest. It also outperforms the diffusion-based line. So there are a lot of diffusion-based versions for image editing, and we outperform that using autoregressive model. So this is the link to the archive paper if you are interested in checking it out. OK. All right. So that was the first part of my talk, which was building an agent, RL-based agent for image editing tasks. Now I'm going to focus more on the multimodality aspect itself, right? So all of these multimodal models, even the models that you're probably using for agents, are trained on lots of multimodal paired data, right? Images and language data. So these are trained on billions of data points, which is clearly challenging for academic labs to train such models. So basically, we were asking two questions here. Can we achieve data efficiency by selecting the most informative data points dynamically? And does such a kind of training induce any interesting curriculum in the learning process? And as you can imagine, the answer is yes for both the questions. So this is a paper on arXiv, which is under review right now, collaboration between my lab and Leonard's lab at UBC. So here we are working with these kinds of models like Lava, which are multimodal large language models, and they are built for doing tasks like image captioning or answering questions about images like the one shown here. And this is again just to reiterate the point that when you're building multimodal models, then you need paired data, right? You need images and captions data, but specifically when you're doing instruction tuning, you actually need to employ humans who can write questions and answers about images, or you can use models like GPT to generate those kinds of questions and answers, but that also is financially expensive. And this is a plot just showing that if you look at across the years, the increase in the compute, so you will see models which use multimodal data, GPT-4, Gemini, are sitting at the top of this list, right? So it is quite expensive. So we are going to focus on these kinds of models and try to improve the data efficiency, specifically in the instruction tuning stage. So just to give you, an idea of the architecture of these models, so basically, the architecture looks like this, where you have a vision encoder, typically, let's say, clip-based vision encoder. Then you have a projection layer that projects those vision embeddings to be consumed by your large language model. And here you have a large language model sitting on top. And then after that, if you have a question, you feed it to your large language model, and then you start generating a response, either the answer or the caption and so on. So there are typically 3 stages of training involved. The first is just pre-training your LLM and simultaneously pre-training your clip model. So this is not that difficult because you have a lot of data available. And then the second stage is pre-training your projection layer, or MLP. So again, this is also done using paired data, but you can mine data from, like for example, conceptual captions data set is a popular data set, which is just obtained by mining web pages and the images and the associated text with that. But the most expensive stage is the final stage, which is the instruction tuning. And as I said, in instruction tuning, you need questions and answers, and these need to be high quality, so this can't be very noisy. And in this paper, for example, which set the trend for instruction tuning, they use human data and also data generated by GPT. So yeah, we don't want to, perhaps the hypothesis here is perhaps not all of these data points are very useful. There are some very easy samples which offer limited learning value to the model, and then there are some hard samples which actually model is just not yet ready to learn those samples. So can we find these, the right samples which the model will benefit the most when learning from those samples? And we want the large language model to identify those samples itself, right? Like we want to do it dynamically, because as the training is progressing, the model's capabilities are also improving. So basically, this is the framework that we proposed here. So this is inspired by active and curriculum learning, and we propose this self-evaluating training framework. So the first stage involves basically you take your training data set and then you do some concept categorization. So, and the reason for doing this is because we don't want to track the model's accuracy or loss on individual data points. We want to track the performance at a level of skills, right? So is the model doing well on counting? Is the model doing well on color recognition, OCR, reasoning, and all of that, right? So we take our pool of images and questions, and we just do clustering using the joint embedding coming from Dino, which is an image embedding model, and BERT, which is a language embedding model. And we obtain very nice clusters. So if this is to show that if you do the clustering based on either just the image embeddings or just the language embeddings, then you don't get very tight clusters. But if you do it based on both, then you get very tight clusters. So here you see, all the data points are about giraffe, but also a particular kind of question about giraffe, asking to provide the bounding box coordinates. Similarly, on the right, all the images are about books, and all the questions are about OCR recognition. Okay? And then basically, the way we do this selection is keeping track of the accuracy change for these clusters over iterations, and we actually keep track of relative accuracy change, because basically, if the model is already, let's say 10% gap for easier skills is not as effective as a 10% or 10% improvement for harder skills, right? So we want to encourage that. So yeah, this is our selection function. We are just basically asking the model to prioritize those clusters where the accuracy change is higher with respect to the current level of proficiency. And we only require answer annotations for these data points that we are selecting. So we don't need annotations for the entire corpus, right? We decide which data points we want to train on, and then we need answers. So it's basically efficient, not just in terms of compute, but also in terms of annotations requirement. And long story short, basically this model achieves state-of-the-art performance on different architectures and different data sets. But the punchline here is this performance is achieved with only 20% sampling ratio, which basically means that only with 20% of the full data, we are able to achieve performance which is close to the full fine-tuning performance. And there are a bunch of other methods which are also trying to solve the same goal, and we show that we outperform those methods as well. And one way in which we are particularly better than these existing methods is that they require full answer annotations. We don't require full answer annotations either. And we show that this method doesn't show performance improvement only for this particular model and particular data set we tried. It generalizes to other model architectures as well, generalizes to other data sets as well. And finally, one question that you might ask is how effective is this selection function that you have designed? What if you always select the clusters where the performance is lowest? So those are the easiest, the easiest selection function. What if you select the clusters where the performance is, the highest? Sorry, the first one was hardest. What if you select the clusters where the performance is highest? So that is the easiest, and so on, right? So just to check whether this choice of selection function, how much does it matter? And then you can also look at this performance based on looking at basically your benchmarks, only the hard benchmarks, easy benchmarks, and so on. But basically what we found is the selection function is better than all the other selection functions across different types of difficulty levels. And remember, in the beginning, another question we had asked is, if we do this kind of dynamic training, then does that lead to emergence of any interesting curriculum in the way the model decides to select examples and trains? And so this result is not super clean, I would say, but we did see some interesting patterns. So here what we are looking at is, on the x-axis you have the progress of training, right, training iterations. And on the left y-axis you have how many samples the model chose at a given iteration of training for a given skill, right? So for example, this tells you how many samples of text translation tasks the model decided to train on, how many samples of OCR the model decided to train on, and so on. And on the right y-axis, you have how the accuracy is improving for that particular skill over time. So for OCR, it's actually quite interesting pattern. So you see that so if you look at the number of samples that the model chooses for OCR is less in the beginning, but then it increases the number of samples. And when the number of samples increase, the accuracy also, you see, starts going up, right? So that's interesting to see. Like, it basically decides to prioritize learning OCR towards the end of training. Similarly, more complex tasks like text translation and code reasoning also it decides to learn towards the end of training. So overall, we basically, in this case, we're proposing a dynamic framework for selecting the most informative samples during instruction tuning stage. And as I said, our method achieves full data performance using only 20% of the samples. And it induces curriculum learning, which, it's a bit expected that it will prioritize more difficult samples towards the end of the training. And again, you can check out the paper on arXiv here. All right. Okay, so with that, let's move on to the third part of my talk, which is how do we assess to what extent the behaviors of the model or the predictions of the models, multimodal models, are aligned with human expectations. So here we are going to look at text-to-image models, so image generation models, and we are going to look at their alignment with respect to cultural prompts. So what do I mean by that? So let me show you an example. So here, the prompt is generate an image of a housewarming ceremony from India. And to give you an example idea of what a housewarming ceremony looks like, so it typically looks like this. People gathering, there's certain kind of decoration in the house, certain beverage being heated up. That's milk, I guess. But when you prompt a model to do this, it generates something like this, which is an image of a house literally being warmed. So there are a bunch of these traditional elements that are missing from this image, right? So that basically shows that these models are not very culturally aware. And here is another example prompt, Muslims breaking fast during Ramadan in India, and a model generates this. So one other thing you can do is just feed this prompt and the image to GPT and ask whether the generated image is faithful to the prompt or not. And it actually says, yeah, it's pretty faithful. It depicts a group of people breaking fast during Ramadan in India, suggesting a cultural setting similar to India. Minor details might not be perfect, but overall, it's pretty effectively following the prompt. But now, take some humans, right? Ask some humans who are from this culture, Muslim culture in India, and ask them, how do they think about the image? They are not happy. They say, no, the women in the images have bindi. So bindi is like a red thing that you put on your forehead. It's a cultural element from India and maybe some other cultures as well. And it says Muslim women don't put that, so it is actually wrong. This is wrong depiction. And women are wearing hijab, but they're wearing it in the wrong way. So, this is not good. So clearly, these models are not meeting the expectations of humans for these cultural, different cultural scenarios, right? So we were interested in asking how effective can we quantitatively assess how effective current models are in meeting cultural expectations from different countries. And here we are using country as a proxy for culture, which actually is, has some limitations of its own, but we're not going to get into that for now. And how effective are automatic metrics? Because for a lot of these image generation tasks, we use automatic metrics to determine whether the output is good or not, right? So we are also going to evaluate the goodness of the automatic metrics, specifically how aligned those are with human evaluations. So this is a paper which is going to be presented at EMNLP, and this was done in collaboration with researchers from Google and also students from Siva's group. So yeah, here basically the key aspect that we were interested in is evaluating, systematically quantifying or evaluating the alignment of these text-to-image models with respect to both explicit as well as implicit cultural expectations, and this is a new angle that we are bringing to the table. People haven't looked into this before. So what we mean by explicit versus implicit expectations is basically, explicit expectations is just checking whether the generated image is, faithful to the concepts or to the words that are clearly stated in the prompt, right? So whatever has been clearly stated in the prompt, is the model following that or not? So for example, here, if the prompt is people offering flowers to Saraswati statue, then you can ask, are there any people in the image? So these are the things that the model needs to satisfy to be able to satisfy the explicit expectations. Are there people in the image? Are people offering something? By the way, Saraswati is the name of the idol, the goddess whose idol you see here. Are people offering something? Are there any flowers in the image? And so on, right? Now, when we come to implicit expectations are, things that are not explicitly stated in the prompt, but are still expected to be present in the image because of the cultural context it is in, right? So the model needs to have the cultural context to be able to satisfy these implicit expectations as well. So for the same example here, for example, one would ask, is the setting appropriate, right? Does it look like a religious ceremonial setting? Are the people dressed in an appropriate way? So for example, in India, you can't, for ceremonies like this, it is a bit offensive to wear revealing clothes. So you can't be doing that here. Is the Saraswati statue depicted correctly with the classical features, like a particular kind of cloth and all of those things? So basically, we wanted to have this comprehensive evaluation with respect to both explicit and implicit elements, and we built a very thorough data collection pipeline for that. So first, we decided that we are going to work with these cultural categories: religion, greetings, family, etiquette, dates of significance, and so on. And Cultural Atlas is a repository which tells you what are some norms for each of these different categories for a bunch of different countries. So we took those norms, so these are like assertions in language only, and then we prompted GPT to generate prompts that can be, that will be relevant for image generation models. So basically, we wanted to, the prompts should be such that they depict visual elements, right? So they should be visual in nature. And then we took a bunch of state-of-the-art image generation models, including the ones from, Gemini and GPT-4, and we basically went to humans and then asked them to do very detailed ratings with respect to both explicit and implicit elements. So for example, here, this is the prompt: Iranian family serving saffron rice during a commemorative meal. And then we ask humans to first tell us, what is the score that you will give with respect to the image prompt alignment criteria. So how faithfully does the image align with the prompt? And then if they give a score which is less than 1, we ask them to identify what elements are missing. Is it explicit, implicit, both? And then we don't stop there. We ask them to also tag the words in the prompt with respect to which the expectations are not being satisfied, right? So which word? So is it Iranian part that is not being satisfied? It is the family part that is not being satisfied. And then further, we ask them to give us qualitative comments on why they think certain things are not being satisfied, right? So we wanted to have like really deep annotations from humans, really thorough annotations from humans for this criteria. We also had other criteria like image quality. So here they had to give a score and also had to identify what aspect of image quality is not good. And then also, is the image that is being shown is stereotypical? And if yes, then why is it stereotypical? Right? So that is sort of the core of our contribution, which is collecting all this really comprehensive annotations from humans and then designing the prompts for this. And now let's look at some of the examples here with human annotations. So a bride and groom exchanging vows at the Hindu wedding in India. Now humans basically are checking with respect to each part of the prompt whether this is correct or not. So bride and groom, yes, this is how bride and groom in a typical Hindu ceremony, this is how they are depicted. Exchanging vows, this is not quite right because it seems like they're exchanging vows, but in a Hindu wedding it doesn't happen like this. Is it a Hindu wedding in India? Yes, looks like it. Now, when we go to implicit elements, so people have flagged that vows without a priest is incomplete. And the image lacks sacred fire. So in Hindu wedding, it is weddings are usually around a fire, which is considered a sacred fire, and that's an essential element of the ritual, right? So here, people are really talking about the details that the models have missed. Similarly, here is an example from Chinese culture. Chinese family sharing Peking duck in a bustling Shanghai restaurant. Does it show Chinese family, Peking duck? Yes. Is it a Shanghai restaurant? Cannot tell just by looking at the elements in the image. And then people start talking about other cultural expectations. Typically, you also get served with pancakes and other condiments. So the image is missing that. And Chinese people don't usually use forks and spoons, they use chopsticks, so that part is also probably not correct, right? So it's interesting to, by the way, like I really learned a lot about different cultures by working on this project. So that was the most exciting part to me. So, all right, so here are some statistics of the data sets we collected. We had around 1,000 prompts. We included 10 different countries and the 5 categories: etiquette, religion, family, greetings, and dates of significance. We evaluated the following models: Flux, Stable Diffusion, Immersion, and GPT image. So overall, we generated around 4,000 images, and each image prompt pair was, I think, evaluated by 3 humans. So overall, we have 10,000 ratings from humans. And then we can look at, based on human evaluation, how do different models perform here. And basically, we see that this is the score with respect to the image prompt alignment criteria. So GPT image and Imagen actually are not that bad, but then the other models are still, there's significant room for improvement here. Same for image quality. Here we see that the Imagen performs better than GPT image with respect to image quality. Stereotype score, so here lower the better, because we are just asking whether the image is stereotypical or not. And we see Flux actually is much better than the other models. Then yeah, we can compare overall with respect to the overall score, which combines all of these 3 criteria. See, GPT is the winner. And then you can also sort of compute the correlation. So which of these 3 criteria, so by the way, this overall score is something humans are giving. So, we ask them questions with respect to each of the criteria, but we also ask them overall, what do you feel about the image, right? Give us a score. And then we can compute the overall score, overall evaluation of humans. What is that biased by? So that actually is most correlated with the prompt alignment. So they care most about the prompt alignment more than they care about image quality. And then we can compare the performance disparity of a given model across countries, right? So we're showing the breakdown of performance across countries for each of the models. So you see there is a good disparity across countries, so the models do not perform well across all the countries equally. And particularly, you see Asian countries, including Japan, Iran, China, India, are consistently in the bottom half for all of these models, right? So that tells you what are the weak points of these models. And if we did further analysis, so which aspect are these models failing to capture with respect to explicit versus implicit criteria? So the percentage of times they fail is, let's say, 44%. And then out of these times they are failing, the percentage of explicit errors is 50%, and that of implicit errors is 31%, and both is 17%. But another interesting thing we found is for Eastern countries, the percentage of implicit errors is much more than that for Western countries. And I'm going to skip this plot here in the interest of time. Now, this is the most interesting part. So if you ask humans, what are the aspects that are misrepresented in the image? These are some of the examples that we pulled out from the data set. So for example, I believe this was for Iran, Muslim women don't wear men's Muslim cap and don't put dots on their forehead. For Chinese, they are not Chinese-style graves. We do not use these offerings. These are not Japanese sweets. And people from Iran particularly felt that their culture is being not depicted properly. In my opinion, it is cliche to put a hat on all people. Iranian women do not wear hijab with their immediate family, and so on. I'm going to skip this as well in the interest of time. And the last thing we looked at was evaluating the metrics themselves, whether the metrics correlate poorly with human judgments or not, and we actually found that was actually the case. So some metrics are good. VIE score is actually the best, but a lot of the other metrics we evaluated correlate poorly with human judgment. And basically, there are a few other things we did, but I'm going to skip that again in the interest of time. So there are a few more details on evaluating metrics. But overall, basically, here we proposed a novel benchmark for evaluating cultural expectation alignment. And we found that both models and metrics fall short of meeting the expectations. And again, you can check out the paper on arXiv. So that brings me to the end of the talk. But before I conclude, I want to give shout out to 2 other papers, which actually are more relevant to the theme of this workshop. But I did not cover that because I wasn't closely involved in those works. So this work is led by my student Shravan as part of his internship at ServiceNow. This is a paper at ICML. And here, they actually build a benchmark for evaluating desktop agents. And it's a very comprehensive benchmark, covers multiple tasks, so you should check that out. And the main finding here is the grounding aspect is the most problematic aspect for these models, especially when it comes to identifying smaller regions in the interface. This is another paper led by my student Le, which will be presented at EMNLP. So here what he did was he built a reasoning-based re-ranking agent based on the list-wise re-ranking strategy. So the idea is to employ reasoning for re-ranking, and found, again, using GRPO, and found that that's quite effective. So the proposed method surpasses or matches GPT-4 performance or Qwen performance on a bunch of tasks. So with that, I'll end my talk. We talked about these 3 different things, and happy to take questions if we have time, or reach out to me on my email. Thank you.
Great. I think maybe we have time for one question. So maybe come up to the mic stand or raise your hand. OK.
Hi. So thank you so much for the presentation. I have a question regarding the editing paper. So how do you train the cases that have ambiguous prompts? For example, remove 4 balloons after out of those 7 balloons as 35 correct solutions. So I was wondering how do you train those cases? Thanks.
I'm not sure, I did not fully hear the prompt, but there can be 2 types of ambiguous prompts. One where even for a human it is hard to understand what the prompt is about. I believe we did not have many of those kinds of prompts. The data sets we were using were of reasonably good quality. But then if you're talking about prompts which is under-specified, so if you say, okay, remove 4 out of 5 bottles, or like remove 4 out of 7 bottles, but it doesn't specify which 4 bottles, we did have those kinds of prompts. And here basically, any 4 bottles it removes is fine. So model has to just reason about it in itself. It has to decide by itself. So yeah, we did have those kinds of prompts, and yeah.
Sorry, I was wondering, what is the ground truth for training those? For example, so you were showing one image and one output, if the network is...
Yeah, so for the SFT case, we do have a ground truth edited image, and there we have just one ground truth. So yeah, ideally you should show all possible ground truths, but here we just have one. But for the RL case, we don't have any ground truth, right? So it's basically whatever prediction the model generates, the verifier should be good enough to identify that whether certain number of bottles have been removed or not. So yeah, so in this case, verifier was doing a reasonable job. But I should mention that, verifier is also not very good in terms of counting and spatial reasoning. So there was only so much of a performance we could improve with not a perfect verifier.
Great. OK, now I think we'll take a break. Thank you so much, Aishwarya, for the great talk.